There we go. Okay, so this is Tuesday's class, and no, Wednesday. This is Wednesday's class, and the first thing I had on the board for people as they came in was the answer key to page 22. So here it is. There's a link to it on the blog as well. Number 4, you should have got 1. For number 5, this one was a little tricky. You had to actually do the rationalization, but then you get a quadratic. I factored the negative out of the quadratic to make it easier to factor, and then that's what cancels the x minus 3, is the factoring of the quadratic. And then once I was done, I got negative 5, 6. Very easy to lose track of that negative. Be careful with that when you get ones like that. And then for number 6, that was just sort of fraction work and then factoring again, and I got negative 2/27. Okay, so I'll just leave that where it is. And then we're going to go to our notes package today, and we're going to pick it up on page 23. Okay, let me get to my OneNote. There we go. And today's topic is one-sided limits. This is a short little lesson. And it starts with one more reminder of the stuff that we've seen like 10 times now, right? How do we find the limit as we approach a hole in the function? Because we know that f of x doesn't exist at x equals 2 because f of 2 is undefined, right? Because if you plug in a 2 for x, you get 0 in the denominator. So I already did some number crunching here. I tried what happens when x is 1, and I get 3. At 1.5, I get 3.5. And then by 1.9, I'm getting 3.9. And then every time I add a 9, I notice the pattern, well, I'm just slapping 9s at the end of 3.9. And if I approach it from the right-hand side, something similar happens. If I start when x is 3, I get 5. And then 2.5 gets me a 4.5. 2.1 gets me a 4.1. And then a 4.01. And if I kept adding zeros in there, it's just going to keep adding zeros in here. So it's for sure, I can say that the limit as x approaches 2 of x squared minus 4 over x minus 2 is very definitely 4. Now, not all of the limits we're going to do work out that nicely because they're not all holes. So sometimes you have to think about limits as coming from two directions. I mean, we did. We approached it from the left. We approached it from the right. But let's define what it is to actually just do one of those at a time. The left-handed limit, if the values of f of x approach L as x approaches a from a, any value a from the left, i.e. x approaches a, and then put a little negative here, and that means you're coming from the left-hand side. We say that the left-hand limit as x approaches a is the limit L. And then a right-handed limit is if the values of f of x approach L as x approaches a from the right. In other words, symbolically, x approaches a from the right. Then we say that the right-hand limit as x approaches a is L. So if I have just any old function, just some curve, just make me a kind of a generic curve, would you? And we have a point here, and maybe the point's a hole, maybe it isn't, but that point is when x is a. Well, if I'm approaching from this direction in my calculations, I'm saying that x is approaching a from the left. And if I'm approaching from that direction, I'd say x is approaching a from the right. So that's how you think about those symbols. And of course, this value here, this y value, is L. Now, it's super easy to get this mixed up. I know, there's already people, I can see the look of disbelief in your face. It's like, wait a minute. All the time that we've been doing coordinate geometry since grade 7, we've been thinking, or even number lines, go back to elementary school, number lines. If you're going to the left, isn't that the negative direction? And yet, if I'm going this way, when I think about my limit, we put a little plus. We're approaching it from the right. So think about the direction you're approaching it from, right? Where your starting place is. I'm starting on the right-hand side of the place I'm doing the limit at, and the right-hand side is positive. If I'm starting on the left-hand side, the left-hand side is negative. Don't think about direction. Think about where you start. That might be the best way to explain that. All right, anyway, the first law of limits is that if I approach from the left and I don't get the same value for the limit when I approach from the right, I would say that the limit at A does not exist. But if I approach A from the left, I approach A from the right, and I get the same value, L, the limit does exist. And that's true even if the function itself doesn't exist, right? This one had a hole there, but it still has a limit of 4, because that's the number I approach from the left and from the right. Second law of limits, given the first law and the definitions above, we can see that even if the limit as x approaches a equals L, that does not mean that f of a equals L or that the function even exists at a, right? So for example, let's say that we're looking at f of a is equal to some point, is some y value L, right? When I plug in a to the function, I get L. Well, in this diagram here, as I approach a from the left, it's heading towards L. As I approach it from the right, it's heading towards L. So I would say that the limit as x approaches a is whatever this L value is. Now, we actually haven't seen one like this before, but this has a hole in it. But at that spot, when x is a, this dot, this point represents the value, which I guess would be L, looks to me like f of a. Let's assume these are counting by ones. That would be L minus 1, right? Because if this height here is L, this height here is L minus 1. But when I approach this hole from the left, I'm approaching the value L. When I approach this hole from the right, I'm getting infinitely close to L. So even though at the actual point A, when I plug A into the function, I'm going to get L minus 1, the limit is still L. And then, of course, there's the more traditional, there's a hole in my function. So f of A does not even exist. It's undefined. But when I approach it from the left, I'm approaching L. When I approach it from the right, I'm approaching L. So since those two things agree with each other, the limit is L. Okay. In all three cases, we get L. Whether it's a continuous function, like the one on the left, whether it's a hole, but it jumps to another value, which, by the way, we're going to call a jump discontinuity. That's tomorrow's lesson. Or whether it's just a traditional hole, which we're going to call a removable continuity. All right, or sorry, a removable discontinuity, I should say. So there's example 2. Now look at that interesting looking thing. Okay, so let's see what we can think about this. The limit as x approaches 0 from the left. Remember, that negative means from left, so I'm thinking about this one. It looks to me like I am approaching the value, I guess, is that 3? As x, oh, sorry, as x approaches 0, my bad. As x approaches 0, so we're approaching the y-intercept. I guess that's about 3.5, eh? There we go, we'll call that 3.5. What about as I approach from the right? 3.5. I mean, it's continuous, right? So the left and right limits agree. So I can say that the limit is 3.5. And f of 0 does look like it is 3.5, right? If I plug 0 into this curve for x, I get 3.5 for y. All right, next point. What about 1? What if we approach 1 from the left? Well, if we approach 1 from the left, we look like we're approaching 3. If we approach 1 from the right, we're approaching 0 because we're hitting the x-axis. So what do we say about the limit? If we approach from the left and we approach from the right, we get two different numbers. So we'd say that this limit does not exist. I'll put a little star by that. Does not exist. Okay, somebody's asked me to repeat this. So, as I approach x is 1 from the left, I'm definitely approaching the value 3, right? I'm getting infinitely close to 3. It doesn't actually exist there, but I'm getting infinitely close to it. As I approach from the right, I'm getting infinitely close to y is 0. Are those two numbers the same? No. So the limit doesn't exist at x equals 1. Okay? F of 1, by the way, how much, this is a function in two pieces, or actually I guess three pieces if you include this dot that's kind of out by itself. What is the actual value of the function when x is 1? And the answer is 0. How come the answer is 0? Because this is a solid dot, and this is an open dot. That's something you were supposed to learn back in grade 9 when you were drawing number lines. We represent a value that you get infinitely close to without touching with an open circle, and we represent a value that you are actually at with a solid dot. All right, what happens as we approach 2? Well, as we approach 2 from the left, looks like we're heading towards a y value of 2. As we approach it from the right, we're getting towards a y value of 2. So we can say that the limit is 2, even though the actual value of the function at 2 is this dot down here, which is 1. All right, one more example. All right, there's another function that's all jumpy all over the place. What happens as I approach 0 from the left? Well, it looks like I'm heading towards 0. What happens as I approach it from the right? From the right, I'm heading towards 2. So what do I know about this limit? It does not exist. All right, how about when x is 2? As we approach it from the left, looks like we're heading towards -2. As we approach it from the right, looks like we're heading towards 0. But once again, those are not the same numbers, so it does not exist. How about 4? Well, as I approach x is 4 from the left, looks like I'm heading towards y is 4. As I approach it from the right, I'm heading towards y is 4. So that limit is 4. Now what about the actual values for the functions? Read the dots. How much is the function's value for y when x is 0? This is a whole. That's the value that counts. It's 2. For the next one, what happens to this function when x is 2? That's a whole. That's the one that counts. So -2. And of course, that's a whole, and there's no other points above or below it. So it's undefined, or again, a synonym for undefined is it does not exist. And that's really all there is to this little lesson. And if you were stuck on number 1, hold on a sec, I'll get to your question in a sec. If you were stuck on number 1 of that homework assignment I gave the other day, let me just go back to it here. There we go. And there. If you were looking at this question going, I don't know what the heck to do with this thing, that's what these examples today were for. So that's why I said you might want to just, oh, sorry, it wasn't even that one. It was this one. If you wondered, like, how can it have two different pieces to it? And how can there be a hole here? Well, that's because some functions stop and start. And now the assignment is 1.3, and in 1.3 you're going to have ones that have multiple places where they stop and start and jump around. And you might be asking yourself, you might say, self, what on earth would the equations look like that'll make lines like this? Well, actually you saw them back in grade 11. Do you remember what a piecewise function is? A couple couple people are nodding. Everybody else, that'll be tomorrow's lesson. We'll take a quick look at quick grade 11 review at piecewise functions. So that's basically it for today. That's the lesson for 1.3. So if we go to the blog, you can see that I'm saying that you can still keep working on 1.2 if you're still working on that, but because exercise 1.3, there's a second part to the lesson that we're going to do tomorrow, but if you're done the 1.2 assignment and you want to get started, you can try the 1.3 tonight. Before we wrap it up, maybe one last thing. I did take the examples from, let's see, what was it again? Page 22. The ones that I left you with yesterday to try. There we go, page 22, this page here. I took these 3 examples for 4, 5, and 6, and I did graph them. And that's not a bad thing to do. Like if you're not sure of your algebra, let me go back to the actual key here. Where are we, key? There we go. If you're not sure of your algebra, if you're looking at this going, I got negative 5, 6, but I don't know if negative 5, 6 is right. And of course, there's no answer key for this. You know what you could have done is, again, you could have gone to our old friend Desmos and graphed the equation. So here, that's the first one. There it is. And say, okay, what happens as I approach 3? And as I get closer and closer to 3, now unfortunately Desmos doesn't give you fractions, but you can just take your calculator and realize that 5, 6 is 0.83 repeating. And as you can see, I'm getting very close to 0.83 repeating. 0.831, 0.832, 0.833. And of course, if I go right on it, I'm going to say undefined. But as I get very close to it, it checks my answer. Right, so let's see, what was the other one that I had? The third one was negative 2/27. So I might take my calculator out and try to figure out what 2 divided by 27 is. So let's see, I'm using my calculator. 2 divided 27, 0.07. So I'm going to go back to Desmos here and I'm going to say, okay, how close does this get to 0.07? So there's the third one. And as you can see, when x is 3, 5, 4, 3, okay, it was undefined at 3. And there it is, undefined. Come on, undefined, there we go. But as I get infinitely close to it, 0.07. So yeah, we've got the right number. Okay? So the person who messaged me yesterday saying, I did the page 22, how do I know if I'm right? Try them on Desmos. Drag your point around, see if you get close to the answer that you think you should get. Okay? All right, I'm going to stop the video here, and if there's any questions, I'll take them.